Hi folks, Chris McClure here. Now we're going to talk about measures of relative standing and box plots. Now, when we're talking about relative standing, we're talking about where in the distribution of data is a particular data value. And we could talk about using this ideal of relative standing to compare values uh, within the same data set or between two different data sets. In particular, we're going to be looking at percentiles and z-scores. And lastly, we'll take a look at box plots. So first of all, z-score. The z-score is the same thing as a standardized value. And it talks about the number of standard deviations that a given data value x, we can call it X or Y or whatever, any letter of the alphabet, we typically use X as our data value. But Z refers to the number of standard deviations that data value is above or below the mean. It could be a negative or positive number. Here's the calculation. If we're talking about a data value within a sample, then we need to know the sample mean, X bar, and we need to know the sample standard deviation, S. Then for that data value in question, X, we just take that data value, subtract the sample mean, and then we divide by the standard deviation. Now, if we are talking about a population and an observation within a population, and we happen to know the population mean mu and the population standard deviation sigma, then to find the z-score for our data value x, all we need to do is subtract the mean and divide by the standard deviation. We typically don't do this unless we're talking about a theoretical sort of discussion for a data value. And we'll talk about this later on when we start talking about normal distributions. We'll typically talk more about the sample standard deviation or the sample values and finding their z-scores. We typically round z-scores to 2 decimal places. Now remember when I told you last time that any data value, any observation that is, beyond 2 standard deviations from the mean, then that's considered to be an unusual observation. Well, the z-score is the number of standard deviations that a data value is relative to the mean. So if the z-score for an observation is within 2 standard deviations, meaning between -2 and +2, then that data value is considered to be ordinary. But if that z-score is less than -2 but greater than +2 or greater than +2, then that's an unusual value. So let's take a look at this example here. Suppose that we have this individual with a pulse of 48 beats per minute. And that seems to be rather low. But is that unusually low? Well, what is the average pulse rate for adult men? And what is the standard deviation? Well, suppose that we assume an average or mean adult male pulse rate of 67.3 with a standard deviation of 10.3 beats per minute. Then we can calculate the z-score for the 48 beats per minute, which is the pulse of the author. 48 minus 67.3 mean divided by 10.3, that's -1.87. And notice that this z-score is not less than -2. It's greater than or equal to -2, but less than +2. So that means that the pulse rate of 48 beats per minute is not unusual. Now we're going to talk about percentiles. Now, if you had taken a standardized test, so for example, the GMAT or the SAT, when you got your scores in the mail, you were given your score and you were probably told your percentile. And your percentile, which is given to you as a percentage, will tell you that you scored better than a certain percentage of the population. So for example, if you got a score at the 87th percentile, that means that you scored better than 87% of everybody else who took that same test. You will not see percentiles as fractions of percents. You'll only have integer values of percents. 1%, 2%, 3%, ... 85%, 86%, and so forth, all the way up to 100%. So there are 100 groups with about 1% of the groups in each, or 100% of the values of the population in each group. Now, suppose that you have that test score and you want to calculate your percentile. Then what you need to do is count how many people who scored less than you, divided by the total number of people who took the test, times 100. So for example, if there were 87 people who scored less than you out of 100 people, who took the test, well then 87% 87 will be your percentile, because you're going to have to take 87 over 100 times 100, and you'll always get a positive integer between 1 and 100, including 1, including 100. You may have to round up, by the way. So let's look at this example. Suppose that we've got this data set that you saw last time. We have 40 cookies from Chips Ahoy, and each data value is the number of chocolate chips in a cookie. So we saw that there was a cookie with 19 chips, another cookie with 19 chips, another cookie with 20 chips, and so forth. We've got the data set sorted from smallest to largest. That's something that you have to do in order to do this right, is sort your list from smallest to largest. So suppose that we wanted to find the percentile for a cookie with 23 chips. Okay, so we locate the first occurrence of 23. And then we count the number of values smaller than 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right here. So there are 10 data values smaller than 23. So you take 10 divided by the 40 cookies times 100. I promise that this little square right here really does mean times. There's a little typographical error, but so this works out to be 25, right? 10 divided by 40 is 0.25 times 100 is 25. So that means that a cookie with 23 chips is in the 25th percentile, because 25% of the cookies in the sample have less than 23 chips. Okay? Now, if we wanted to go in the opposite direction, and you happen to be looking at a particular percentile, and you want to find the position of a particular value, then you can kind of work backwards. So L is going to be that locator that gives the position of a value. K is the percentile being used, and N is the total number of values in the data set. So for example, if you're at the 87th percentile, and say, there were 1,000 people who took the test, 10,000 people who took the test, 87 times 100, or divided by 100, is 0.87. 0.87 times 10,000 will be 8,700. So what you would do to locate where you are is to do what? You would count, in a sorted list, 8,700 places from the smallest to the largest, and locate your test score. And in fact, I'll show you exactly how to do this. Here's kind of the flow chart. And converting percentiles to data values. So again, make sure that your data set's sorted. So again, think about your mental model here being a long list of test scores. And you want to find what your test score is if you know what your percentile is. K is going to be your percentile. So suppose that K is 87, and N will be the number of test scores. Suppose that N is 10,000 and K is 87. So this calculation here will be 8,700. So L will be 8,700. The question is this result a whole number? In our calculation, the answer is yes. So what this tells you to do to find the value of the 87th percentile for a test score is to look at the 8,700th test score, and then look at the next test score, the next higher test score, the 8701, the test score at the 8,701st one. So you look at the 8,700th test score and the 8701 test score, and then take the average of those two. That value that's exactly halfway between. Hey, they could very well be the same test score, or the 8701st test score could be a little bit higher, but whatever that value is, exactly halfway between the 8700 and the 8701st test score, that's actually going to be that value corresponding to the 87th percentile. Now, if it turns out that when you do this calculation up here and you end up with a decimal or a fraction and not a whole number, then what you'll do is you'll round it up to the next larger whole number. And then that data value is at the Lth value, counting from the smallest in your sorted list. Okay? That's how you do it. That's how you find your data value of the given percentile. Now, we use percentiles from time to time. It's pretty common for us to use quartiles too. Now, quartiles refers to dividing a data set or a population into fourths. And in particular, we have the first quartile denoted by Q1, second quartile, which is Q2, which by the way is the median, and Q3, which is the third quartile, which is halfway between the second quartile and the maximum value. So with Q1, Q2, and Q3, we actually divide the data set / population into fourths. So Q1 is what separates the bottom 25% from the second 25%, or the bottom 25% from the top 75%. Like I said before, Q2, second quartile, is the same as the median. The median is that number that separates the bottom half from the top half. And the third quartile is the mirror image of Q1 in that it separates the bottom 75% from the top 25%. Here's kind of a picture of the quartiles. Here, imagine that you were to arrange all the numbers in your data set from smallest to largest. Well, Q1 will be that number at the 25th percentile. And Q2 will be at the 50th percentile. Q3 will be at the 75th percentile. Divides the sorted data values into 4 equal parts. Now here are some other quantities that we're going to use from time to time. We use the interquartile range, abbreviated as IQR, as the third quartile minus the first quartile. They're just numbers, okay? Semi-interquartile range will actually be half of the interquartile range. The mid-quartile is the average of the first and third quartiles. And then the 10 to 90 percentile range is the 90th percentile minus the 10th percentile. So you might see this from time to time. These are all pretty easy calculations to do. And in your textbook, I think you'll see some examples. And you'll also see some examples in the homework. Now, when we talk about the 5-number summary, this is where we sort a data set from smallest to largest, and we're going to summarize the data set with just 5 numbers. We could talk about its measure of central tendency and its spread, or amount of variation. So here are the 5-number summaries. The minimum value, first quartile, median, third quartile, and maximum value. Now the box plot is the graph that depicts your 5-number summary. Here's how we construct a box plot. We need some sort of horizontal or vertical scale that encompasses the full range of data values. Then we're going to take our 5-number summary for our data set, and we're going to place 5 tick marks. 1 tick mark at the lowest or minimum value, 1 tick mark at Q1, another tick mark at Q2 or the median, another tick mark at Q3, and then the 5th tick mark being at the maximum value. And then we're going to construct a box, a rectangular box that goes between Q1 and Q3. So for example, here's Q1, here's Q3, here's that rectangular box that goes from Q1 to Q3. And here's the tick mark for the median. The median is always between Q1 and Q3. And then we have a whisker, which is a horizontal line that goes to the left from the rectangular box out to the minimum tick mark. And then to the right of Q3, we have a whisker that goes horizontally out to the maximum value tick mark. So I could tell a lot of things. I could tell that for the data set that this box plot is summarizing, that the minimum value is 4.5, maximum value is 22 or 225. I could calculate the interquartile range, the IQR, 113 minus 35, whatever that is. And then here's the median, which gives us a measure of central tendency. I could also tell a little bit about the skewness of this distribution. Notice that we have the median is a little bit closer to the left edge compared to the right edge, and the whisker on the left is shorter than the whisker on the right. That tells me that this data set is going to be skewed right. Here is a computer generated box plot. So if you were to go into StatCrunch and have StatCrunch do a box plot chart for you for a column of numbers, well, it'll look something similar to this. And we should not be surprised that it looks fairly symmetric, looking to the left and to the right. Notice that this median is right about halfway between the left and right edges of the rectangular box. And not only that, the left whisker is just about as long as the right whisker. This data set has to do with heights from a simple random sample of women, which, by the way, is a normal distribution. Heights of women, just like heights of men, is normally distributed. And the normal distribution is symmetric. So we would expect that a sample from that population will have a symmetric looking box plot. Now, if you see a box plot like this, that means that you have a highly skewed distribution. It's going to be right skewed. This data set is going to be salaries in thousands of dollars for NCAA football coaches, where the vast majority of football coaches, these are college football coaches, are, above 125, but less than about 700,000. But they're, as you go to the right, higher and higher toward $1 million and $1.5 million, $2 million, that they gradually drop off. So it's a right skew distribution for this box plot here. Left skew distribution will be the mirror image of this, where you would have this rectangular box over here toward the right, and the median would be closer to the right edge than the left edge of the box. Now, we might choose to identify any outliers. And remember, we talked about outliers before. Outliers are data values that are relatively far away from the rest of the data set. And how do we decide on what is an outlier? Well, I'll show you here in just a minute, but these are some important ideas regarding outliers. They can have dramatic effects on the calculation of the mean and the standard deviation, and also on the scale and shape of the histogram, so that the true nature of the distribution could potentially be totally obscured if you have an outlier. So how do we decide which data values are outliers? Here's the general guidance here, is to create a fence. And the fence is going to be where you take 1.5 times the interquartile range. And remember, the interquartile range is Q3 minus Q1. Now, if you go above Q3 by an amount of 1.5 times IQR, and below Q1 by 1.5 times IQR, then that's going to give you kind of the boundaries, or a fence. Any data values smaller than this quantity here or greater than this quantity here will be considered outliers. So you'll have the chance to practice that in the homework. So you'll calculate Q1 and Q3, take Q3 minus Q1 to find your IQR, take 1.5 times it, add that to Q3 and subtract from Q1, and any data values outside of that range are considered outliers. Now, when we talk about a modified box plot, what we do is we exclude any numbers, any values in your data set that are considered outliers, or at least you highlight them. You don't delete them, but then you compute your 5-number summary with all the others, not including the box plots, and then you construct your box plot based on the rest of that data, excluding the outliers. And then you place a star, asterisk, some other sort of symbol to indicate those outliers. Okay? So that's what this is telling us. So here's an example of a modified box plot. We had identified this number here and this number here as outliers. Now, let's take a look here. Here's Q1. Q1 apparently is about 68. Q3 looks to be about 80. Now, 80 minus 68 is 12. So IQR is 12. 1.5 times IQR is 18. Now, if you were to take Q3 plus 18, 80 plus 18 is 98. So any of these pulse rates that are greater than 98 will be considered outliers. So that's why this one at 102 or 103 is considered an outlier. And this one at 124 or whatever is also an outlier. Okay, did everybody see how I did that calculation? Also, if you were to take this first quartile at 68 minus 18, which is 50, any pulses that are less than 50 would also be considered outliers. So, we've come a long way, wrapping up chapter 3 here. And this is kind of what we have talked about. I'll let you take a look at it. Okay? We're going to start chapter 4 tomorrow, keeping a pretty tight schedule. Now, I'm going to tell you right now, and I'll send an email out probably tomorrow talking about the final exam. I realize that the final exam needs to be given by about the middle of July in order to comply with the course ending date. Okay, so we'll take a look at that on the calendar. It'll be different from what I had put out on the syllabus. Okay, so with that, we're done for today, and we'll see you next time. Okay, so take care, good luck, have a good day.